Hello everyone and welcome to another Würth Elektronik ISAS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is extremely high-speed data line jokes. Our speakers today are Muhammad Ali Khalid and Ashiro Shengasira, who are working as product manager in the field of EMC inductors and RF components at Würth Elektronik ISAS. They will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at isis-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation as well as to the recording of the webinar only in the next few weeks. And now I will hand over to our speaker Ali, and I wish you an exciting webinar.
Hello everyone, welcome to the new Würth Elektronik webinar. My name is Muhammad Ali Khalid, and today me and my colleague Ashiro will be talking about the common mode jokes, especially the ones designed for high-speed digital interfaces. Here is the agenda for today's webinar. We will start with the digital interfaces, differential signaling, and the associated noise issues. Then we will talk about the existing solutions and introduce a totally new technology specially designed for the 2.4 gigahertz noise. In the end, we will compare both technologies and give you some recommendations. The switching speeds of the modern digital interfaces are getting higher and higher. With the high switching speeds, we are now able to achieve very high data rates and bandwidth. These are some of the individual data line switching speeds for the state-of-the-art communication interfaces. You can also see USB 4 specification. It was released in March 2019 last year, and it will be available to users in upcoming months, years. If we look closely at the switching speeds, we can see that the general trend is towards increased frequency of switching. Differential signaling is used for the transmission of data in these high-speed interfaces. So differential signaling method uses two lines or conductors side by side with same current flowing in opposite directions. But why do we use differential signaling for the data transmission? Why not just use one line or conductor? This is because of the inherent advantages associated with differential transmission of data. These are some of the main advantages. Reduced EMI in both incoming and outgoing directions. So any incoming electromagnetic interference or crosstalk from other noisy traces gets distributed evenly between the positive and negative traces, which reduces any change in amplitude that the external EMI issues can cause. And the differential signals also generate their own EMI while transmitting information, just like the single-ended signals. However, because the positive and negative signals in a differential transmission share the same polarity and distance, this effectively cancels out any EMI emission. Lower voltages, differential signals also have added benefit of being able to operate at low voltages than the single-ended signals, all the while maintaining their signal-to-noise ratio. And with low voltages, you get the benefit of being able to use lower supply voltages, reduced power consumption, and reduced EMI emissions. Signal-to-noise ratio will be explained in more detail later in the presentation. High data rates. The decreased voltage amplitudes leads to short rise and fall times, which means faster switching and hence increased data rates. So transmission lines are the specialized conductors which are used for the differential transmission of high frequency data signals like in USB or HDMI. A transmission line is a specialized cable or structure that is designed to conduct RF current. As the frequency gets higher, the parasitic effects of the signal transfer become more pronounced and affects the impedance and the power transfer. Thus, the conducting media has to be appropriately designed. In the slide, you can see a microstrip line, which is one of the most common examples of a transmission line. It basically consists of three layers, which are conducting strip on top, dielectric with a specific permittivity, and a ground plane. The layout of this line can be easily designed by various available RF simulation softwares or with the free to use online microstrip line calculators. Common mode noise is the type of noise that is conducted on both lines in the same direction. In ideal case, the differential lines should be able to cancel the common mode noise at the output, or the noise should be rejected, but in reality, this seldom works. There is always minute differences of voltage or impedance on the two conductors, and there can also be a small delay in switching times on both lines. These small mismatches get more pronounced with increasingly high clock frequencies and the associated fast rise times. Thus, the signals used in the modern data and telecommunications engineering are serious potential source of RF interference that can influence other devices and systems. Now we'll talk about the signal to noise ratio. It indicates the difference of an interference signal related to the useful signal of a circuit. We can also call it SNR. So the SNR compares the difference between the strength of the received signal level and the noise floor. Typically, the higher SNR results in fewer bit errors and higher throughput. And it is important to talk about SNR because it is the reason why we see problems in communication due to introduction of noise. Higher noise leads to lower SNR levels, which can result in antenna descents. Now, descents is the degradation in sensitivity due to noise sources. Generally speaking, the noise floor should be much below the level of the useful signal, but if the noise level increases due to poor SNR, it can make it very difficult for the antenna at the receiver to pick up the useful signal. This phenomena is called antenna descents and is one of the main reasons why the communication failure occurs at 2.4 GHz due to noise. So the 2.4 GHz ISM band is perhaps the most extensively used band for unlicensed wireless devices. With the increase in the switching speeds of digital circuits like USB 3.1 or HDMI 2.0, more and more noise is being generated at higher frequencies. This noise has the capability to interfere with the wireless channels operating at 2.4 GHz band. The switching speed for the USB 3.1 first generation is 5 gigabit per second. This means that the USB circuit is handling data on a very broad spectrum and at the same time radiating noise from DC to 5 gigahertz, which also includes our frequency of interest, that is 2.45 gigahertz. If there is a Wi-Fi antenna or a wireless device operating nearby at this frequency, it can pick up this noise and result in communication failure. Now we will talk about the noise generated by most commonly used USB standard these days, that is USB 3, also known as USB 3.1 generation 1. But before jumping into it, here is a small overview of different USB standards and data rates as background information. As you can see, the standard is way more complicated than we originally thought. So generation 1 means 5 gigabit per second, generation 2 is 10 gigabit per second, and generation 3 corresponds to 20 gigabit per second. But the overall speed or data rate also depends on the number of active lines per standard. Here is an example of 2.4 gigahertz noise generated by USB 3.1 generation 1 transmission. The source for this data is Intel's white paper titled USB 3 Impact on 2.4 gigahertz devices. The USB 3 specification requires the data to be scrambled and uses spread spectrum technique on the clock, which can be modeled as a sinc function, as you can see in the slide. The sinc function is the frequency domain representation for the spectrum analysis, which is obtained by the Fourier transform of the rectangular signal. Important thing to note here is that the data spectrum is very broadband, ranging from DC to 5 gigahertz. The side lobes can be totally ignored. In fact, the design is based on ensuring that the side lobes are neglected. And here is the data spectrum of USB 3 transmit pair signals from a notebook measured by directly probing, and in comparison is the typical Wi-Fi received signal strength. If a wireless device working at this frequency band is placed close to any of the USB 3 radiation channel, it can pick up the broadband noise and reduce the SNR, which can result in antenna descents. Thus, we see that depending on the distance and receiver sensitivity, the noise generated by USB 3 has the ability to potentially disrupt the communication. Now we will discuss some of the basic techniques to keep the electromagnetic interference level or EMI level to minimum when designing the parallel differential lines. So keeping the signal amplitude to minimum means the EMI less EMI as less time is required for changing the signal state. The lengths of the two traces in differential pair should be kept equal. This is very important. And this becomes especially important with higher rise and fall times of the signal. Physical isolation is probably the most obvious technique, since we do not live in an ideal world and isolation is never perfect. And at gigahertz frequencies, the practical isolation values may vary between 20 to 40 dB. A very crude example, which is also related to current times, is COVID-19. Higher isolation means better chance against the pandemic, which in this case is noise. And then is the impedance variation. It should be kept to minimum, which means paying special attention to the width of the traces, coupling and dielectric material, and the layers stack up. Now my colleague Ashiro will take over and he will talk about more solutions and focus on ferrite-based chokes. So I will hand it over to Ashiro.
So hi everyone, thank you Ali. Now we will see some other techniques to mitigate the common mode noise, because even with all the noise mitigation techniques that my colleague talked about, it is unavoidable to have noise-free communication at these high frequencies. For that, we can use different techniques to remove the common mode noise from the system. By appropriate protective circuitry, it is possible to suppress the interference and at the same time let the transmitted symmetrical signal pass unaffected. Perhaps shielding is the most commonly known solution against noise. That's true for lower frequencies, but if we go to higher and higher frequencies at millimeter wave frequencies, the opening in the shielding is a potential source of RF interference itself. For that, we have filter or chokes, common mode chokes as we call, and they are very effective protecting the data lines. They can substantially enhance the characteristic symmetry of the transmission line and thus contribute further to increase interference immunity and at the same time reducing emitted interference. As you can see in the picture, we have ferrite-based filter or choke, which is the most commonly used solution nowadays. And in the purple picture, you can see a totally new technology, which is based on ceramic, but it's still a common mode choke. We will go through in a few minutes. Here we can see a brief comparison between these solutions. On the left side, we can see the shielding. And what we can see is this: it is highly dependent on mechanical design, and due to some openings in the shielding design, the RF noise suppression is compromised at higher frequencies, where the new interfaces like USB 3.1, USB 4 are working. Conventionally, we have the ferrite-based filters or chokes that have been very effective against the broadband RF noise. But as we move towards higher and higher gigahertz or millimeter wave frequencies, we can see the limitations of the ferrite of the material itself in coping with the signal integrity while providing the required separation for common mode noise. Then on the right side, we can see ceramic-based common mode choke that, compared to other possible solutions, not only provides much better noise suppression, but also stable performance for the useful data signal. That's because of the design itself. Here we can see an example of a circuit. We can see on the left side the power supply. It's connected to a load on the right side, and of course connected to ground. Basically, we can see two kinds of interferences: the conductive and the radiated, due to some capacitive coupling. For that, we need a solution to filter that noise. In our case, we are talking about the common mode choke. By selecting an appropriate common mode choke, depending on the frequency of interest, we can solve that EMI problems in our design. We can find different solutions with a broadband attenuation of the common mode noise with a minimum effect on the differential signal. But first, we will go through some basics of how a common mode choke works. So in a common mode choke, we have always the same structure with different designs, but always the same structure. We always have a ferrite core. It's made of different materials. Then we have two windings. Sometimes we have more if we have some different lines, but mainly two windings, and they have to be as symmetrical as possible. Then we have a housing that can be made of plastic or even ferrite itself, and then some glue that we use for fixation of the core or for insulation. So we have two different kinds of components in a signal. First, we have the differential component of the signal, which is our signal of interest. It goes in differential mode. That means that the signal goes through one winding in one direction, then it goes to the circuit, to the different parts of the circuit, and it comes back through the other winding. And due to the winding style of the core, we can see that in both sides a magnetic field is generated. If we use the right-hand rule, we will see that in one winding, the magnetic field is generated in one direction and on the other one in the other direction. So since both magnetic fields are generated in opposite directions, we will see a compensation in the core. Therefore, no magnetization of the core will appear, and therefore no impedance. So in this case, we will not be affecting our signal of interest or differential signal, and it will remain unaffected. In opposition of the differential mode, we have the common mode. This is what we want to filter, the common mode noise. The common mode is generated in the same direction in both windings, as you can see in the picture. If we use again the right-hand rule, we will see that both magnetic fields in both windings will be generated in the same direction. Then, due to the core and the magnetic field, the core will be magnetized and we will have impedance due to the inductance. What will happen? That we will keep the magnetic field inside the core, so it will hit, canceling this noise. And as you can see, we will cancel our common mode noise in the core compared to the differential signal. We have two kinds of winding style in a common mode choke. On the left side, you can see the bifilar, and on the right side, the sectional. The important here is that the sectional, both windings are separated, and the symmetry is not as good as the bifilar winding style. Basically, what we should know and have in mind is that the sectional is used for power lines, for lower frequencies, and for higher frequencies, we would need to use bifilar winding style. On the left side, you can see an example of our common mode choke winded in bifilar mode. And here we will have the best symmetry possible. That means we will reduce the leakage inductance, which is directly related to the attenuation of the differential signal. But in our case, we want to attenuate only the common mode signal. Here we can see a comparison between the different materials, because in a common mode choke, the ferrite can be made of different materials. In yellow, we can see iron. In this case, this material is not used for common mode choke, but for differential, since it can work in the really low frequencies or lower frequencies, as you can see in the picture. Then we would have the manganese zinc, is the most used material in the common mode chokes, and it's for medium frequencies. Mostly it's used for power lines. In our case, we want to work in higher frequencies up to gigahertz, and for that we have a really good material. It's called nickel zinc, as you can see in green. Here we have our existing solution based on ferrite. We call it the CNSW family, and it's a nickel zinc ferrite based filter. It's fully automated winding, so we have the best symmetry possible. And it has a broadband attenuation up to gigahertz, as we will see in few minutes. Then we have a high frequency version for these newer and faster interfaces. We will see a comparison. We have different sizes in our portfolio, from 0504 up to 1812. Depending on the frequency we want to work, we will have different solutions. The working principle, as we explained, is the same. In red, you have the common mode signal, and in blue, we have the differential signal. Basically, it's what I said a few minutes before. We will attenuate the common mode noise, and the differential signal will be unaffected. Here we have a comparison between our CNSW and CNSW high frequency for the for the faster interfaces. As you can see in the orange dots, that's the cutoff frequency at -3 dB. The red line here is the normal version. We can see that the cutoff frequency is already at roughly 2 gigahertz, and in the high frequency version, we don't have the cutoff frequency before 7 gigahertz, and we still have attenuation of the common mode noise. before the resonance frequency. Important here is to know that in the ferrite-based choke, we have a broadband attenuation of the frequency, as you can see, from megahertz up to gigahertz. But in the new interfaces such as USB 3.1 generation 2 and faster, we will see a noise that it's affecting, as my colleague Alec explained, the Wi-Fi and Bluetooth frequency 2.45 gigahertz. Here we could filter that noise, but we would need a higher attenuation, minimum of 30 dBs in our case. And for that, I will come back to Ali, and then we will introduce our new multi-layer technology.
So the Würth Elektronik ceramic common mode filter is the sensitivity improvement solution for your wireless devices at 2.4 gigahertz. This means that potentially the common mode choke can be used, this common mode choke, or you can call it common mode filter, can be used in any wireless communication device which has high-speed digital switching interface. The common examples include smartphones, tablets, notebooks, routers, IoT-enabled devices, etc. The multi-layer design is made up of low-temperature co-fired ceramic material, which is also called LTCC material. It is very resilient and has low losses in higher gigahertz frequency bands. The differential mode transmission and common mode suppression are controlled by transmission lines in the form of metallization inside the LTCC material. Here are the S parameters for this evolutionary filter. Differential mode is almost straight line up to 10 gigahertz and is well within the 3 dB limits. The common mode suppression is more than 40 dB at Wi-Fi and Bluetooth frequencies, and to protect the devices against the antenna descents. So the filter is basically a combination of a low pass and band stop or notch filter for differential and common mode signals. The patented internal structure is quite complex and comprises of layers of metallization to be able to achieve high performance. Consists of 4 different main structures inside. The differential structure is electromagnetically coupled to the reference potential, whereas the reference potential structure, ground structure, and the ground layer are all electrically connected to each other. Here is the equivalent circuit of the common mode noise suppression circuitry consisting of 5 stages. So it's basically a 5th order filter. So the higher order filters provide greater roll-off rates between passband and stopband. As you know, roll-off is the steepness of the filter transfer function with the frequency. So as the stages of the filter are increased, the stopband attenuation gets better and better. Here is an example of WE-CCMF in real-life Wi-Fi throughput test. The 3 different cases of channel loss are shown with the improvements due to WE-CCMF deployment. Higher the channel loss, lower the Wi-Fi performance, but thanks to the CCMF, we have been able to reduce the common mode noise and antenna descents to get the acceptable Wi-Fi performance. This slide shows the S parameter comparison between the ferrite paste and ceramic chokes. We can easily see the broadband attenuation of the CNSW and CNSW-HF compared to CCMF, where we can see the resonance point at 2.45 gigahertz. So the difference here is broadband noise suppression from the ferrite choke and highly focused noise removal from the most commonly used frequency band, that is 2.4 gigahertz. Here are some of the applications where we can apply one or the other common mode choke. These are well-known interfaces, but of course, for each application, the best solution has to be found depending on the frequency of operation, bandwidth, and EMC requirements. As an example, you can see a simple drawing of USB 3.1 circuit with Type-C connector and application of different kinds of chokes on different data lines. So any device, whether it's a smartphone, tablet, router, laptop, gaming console, or any IoT device, is a potential application for these chokes. With the advent of 5G and gigahertz bands getting more congested, it is safe to say that in future we will see common mode noise at even higher frequencies. But there's no need to worry about that because Würth Elektronik, as your EMC specialist, is already working on the design and addition of next generation chokes to our extensive portfolio. Just to give an idea, some of these solutions include removing the common mode noise at 5 or 5.8 gigahertz band, which is another band used for Wi-Fi, while keeping the integrity of your high-speed data signal. That's all for today. Thank you everyone for attending the webinar. Now is the time for questions, so please go ahead with that. We'll switch over to Marcus now.
So, thank you, Ali and Ashiro, for your interesting presentation. And as you have mentioned, now we would like to turn our attention to your questions, and we wait a little until some questions come in. Okay, Ali, so I see the first question. Why only 2.4 gigahertz noise suppression for ceramic choke?
So this is because this ceramic choke is typically designed for this 2.4 gigahertz application. As we see that the frequencies are getting higher and higher, and the more and more noise is being generated at 2.45 gigahertz. So what we need is that in high-speed differential interfaces is more and more common mode noise suppression. So in some cases more than 30 dB, in some cases more than 40 dB, depending upon the application, of course. So in this case, that's why we designed this choke specifically for this frequency.
Okay, so thank you for the explanation. Then we move on and have a look at the next questions. So maybe if we don't answer your question in the live webinar now, we will answer it via email afterwards. Okay, so next question. What is the noise difference between the ferrite-based choke and ceramic choke regarding EMC?
So the ferrite based choke, as we talked before, is more about broadband noise suppression. So where we have a very wide bandwidth and we want to probably filter from hundreds of megahertz to a few gigahertz, then it's a right choice. But if you want a very specific noise suppression at 2.4 gigahertz and you want a very good common mode noise suppression, then CCMF is the right filter for you.
Then next question. Is it viable to use the choke on TX lines and RX lines like TX and RX or TX and TX?
Yes, we can use them on the by TX means the transmitter and the RX means the receiver. So in the, of course, in the transmitter circuitry, yes, it is really good to use the choke so that we don't have, but of course it can also be used in the receiver circuitry if there is a high-speed digital interface working there. So it can be used in any of those.
Okay, thank you, Ali. So as we have a look at the next question, just a hint from my side, you will get the link to the presentation as well as to the recording only in the next few weeks. Ali, can you please explain antenna descents again?
So antenna desense is basically as the name suggests, it's the desensing of the antenna. So the antenna is not sensitive anymore, but sensitive to what? So sensitive to the useful signal. Normally when the antenna is working, there's on the receiver side, and there are a lot of signals outside which are being bombarded over the antenna, but the antenna has to choose the right signal from them. So normally the power of the useful signal is way more than the other noise, and the antenna is able to pick up the useful signal easily. But with if the noise level is high, which means the SNR, signal to noise ratio, is low, means that the antenna cannot differentiate between the useful signal and the noise. So the communication gets disrupted. This phenomena is known as antenna descent.
Okay, so thank you for the explanation. Until what frequency CNSW and CNSW HF can be used?
So the CNSW is the ferrite based choke that we have, and CNSWHF is the high frequency version of that.
Mhm.
So CNSW can be used from few megahertz to up to few hundreds of megahertz, and CNSW-HF, the high frequency version, can be used from few megahertz up to a few gigahertz. But for more specific knowledge of that, you have to see the data sheets, and you can easily see from what point to what point these chokes can be used.
Okay. So, if you have also some questions left after the webinar, just email us at our email isis-webinar@we-online.com. Okay, Ali, so then I see the next question. If antenna sensitivity is less, whether using choke on TX lines would give better result, or using choke on receiver lines would give better result?
Well, it depends on the application, of course, but in my opinion, both are important. So the choke should be used on both lines because both are able to produce the common mode interference that can result in antenna descents. So my suggestion is to use the chokes on both lines.
Okay. So there we have a last question. If antenna sensitivity is lost, what would be the EMI or EMC solutions proposed from your side?
So the first of all is I would say a little bit. So first you have to see where is the noise of the source. Of course, if it's coming from the same circuitry where the antenna is located, it's coming from somewhere from outside. In most cases, with this electromagnetic noise, we see that the power gets very less with distance. So if you look closely, the noise source is nearby the antenna. So that's why the antenna should be a little bit isolated and moved away from the potential noise sources. This is one of the ways. Second is the change in the direction of antenna, seeing because the antenna works with the electromagnetic waves, as you know, and the polarity. So maybe changing the direction makes it a little bit better. But the best way is is the isolation for the to not to have antenna descents.
Okay, so thank you, Ali, for your explanation. And now we are finished with our webinar. If there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Ali and Ashiro, for this great webinar. I hope you will hear us at our next webinar, and I wish you a good day. Goodbye.